Okay, let's continue. So the small cube that I showed, that is the unit cell, and that same thing can be replicated in all the 3 dimensions, and you can build up your material. Okay, so you can have various different unit cells like this for different materials. Okay, and that's why there are many names given to the crystal structures, and every material will have a different crystal structure. Okay, so what I just now drew and showed you is a simple cubic structure. Okay, there may be others like face-centered cubic structure, all right, or body-centered cubic structure, all right, a base-centered cubic structure. Then there will be diamond cubic structure. So there are many cubic structures. Okay, say zinc blende cubic structure. We'll discuss a little bit about cubic structures later if you get time. So So the thing is that if you take a material from the bulk to the small nano size, the cubic structure will not change. That means if a material is of the simple cubic structure, no matter how small you make it, it will still be the simple cubic structure, right? Only thing is that the distance between the atoms, that is what we call as the lattice parameters, distance between the atoms may change slightly. Okay, at the nanoscale, they will become shorter. Okay, because they're compressed, they become shorter, right? So otherwise the crystal structure is the same. The interatomic spacing decreases with size, and this is due to long range electrostatic forces. Okay, electrostatic forces means the attraction between positive and negative charges, and the short range core to core repulsion. That means repulsion between same charges. That means a nucleus will repel another nucleus because they have the same charges. But then nucleus will attract electrons, or an electron will be attracted towards a nucleus because of opposite charges. Similarly, an electron will always try to repel another electron because they are of the same charges. The melting point of nanoparticles decreases with size. This we already discussed. If you remember that the melting point will decrease. So a bulk melting point of 1000 degrees centigrade may become just 100 or 200 degrees centigrade at the nano size. Now, the electronic, I'm talking about the chemical properties. The electronic structure of nanoparticles is dependent on its size, all right? And the ability of nanoclusters to react depends on the cluster size, right? Since the electronic structure depends on the cluster size, so the ability to react also depends upon the cluster size, because all these reactions are happening through the transfer of electrons, right? Either electrons moving this side or that side, that creates changes in phase, that creates changes in structure, that gives rise to new materials also. The large surface area to volume ratio, just a minute, please. Just a minute. Hello? Madam, what? Yeah. Actually, my class at a lowest. My class to call back call. It number. Okay. Okay. The large surface area to volume ratio, we constantly talk about that. Large surface to volume ratio. I already gave you the small calculations also how to do it, right? As S by V is equal to 3 by R for spherical particles, right? The variation in geometry and the electronic structure of nanoparticles have a strong effect on the catalytic properties. Now, what are catalytic properties? So, do you know what is a catalyst? So, catalyst is something that can change the rate of any reaction without undergoing any change itself. That means if something is happening, you add a catalyst, it will happen instantly. But the catalyst will remain as a catalyst, it won't change. Okay? So, the catalytic properties of nanomaterials, okay, strongly affected by the size, because the size directly relates to the surface to volume ratio, okay, and that relates to the electronic structure, the size, okay. Now summarizing what we've been discussing till now, all right, the following factors are key for understanding nanoscale related properties, okay. These basically describe the change in properties in a nanomaterial. So dominance of the electromagnetic forces, that means the interatomic forces in play, all right, the dominance of these, because that's why it becomes very strong. That's why you're saying that the interatomic, the electromagnetic forces increase. The importance of quantum mechanical models, all right. So quantum mechanical, like I said, no, it's not classical mechanics. It does not follow Newton's laws of motion, all right. To a certain extent, it might when it slightly goes to the boundary of the demarcation of nanomaterials with macromaterials, but otherwise it does not. It follows quantum mechanics. Higher surface area to volume ratio is very critical, and the random motion, right? The typical Brownian motion, where you cannot predict the position at any instance of time. So it is important to understand these four factors while researching new materials in the nano size or in the nano domain. Okay, so this is very important. So this is a wonderful saying from a Nobel laureate in physics. He got the Nobel Prize in Physics in 1945. He said, "God made solids, but surfaces were the work of the devil." So you know what the devil does, right? So anything bad is related to the devil. Okay, anything not normal, anything disruptive, right? So the surface actually is the cause of everything. It's the cause of all evil, you can say, or the cause of all reactions happening, right? So the surfaces are what we really need to study properly, because only the surfaces get involved. Surface means a few layers of atoms, maybe 3 layer or 4 layer or 5 layer of atom is called the surface. All right, because these atoms behave differently as compared to the atoms below that, means inside the material, right? So if we study the surface properly, then we can understand how these materials behave. So the importance of the surface knowledge. So everything has a surface, obviously. You know, everything you talk about has a surface. That means it is a layer that interacts with the atmosphere, with the ambient, right? Beside the inside this or below that, whatever is there, they have no direct access. That means your skin is directly interacting with the light, with the oxygen, with other gases. It's directly interacting, right? But whatever is inside, the cells inside, all right, they are not doing that, or maybe to a minute level, only at the surface, a few nanometer deep, they will have the effect. The rest of that won't happen through the surface, right? So all reactions between materials start at the surface. So it has to start at the surface. If the surface gradually gives away, then it will start moving in. All right. Surface atoms are different from the bulk material atoms because they have fewer nearest neighbors. I already said that, fewer neighbors. So if an atom inside will have 7 neighbors, then my atom at the surface we may have 3 or 4 neighbors. All right. Because the surface atoms are different, their energetics must also be different. That means their reactivity, all right, how much energy is needed to remove them from the material. All these will be different as compared to what is inside, right? Inside the material as a core material. So talking about surface tension now. Okay, this is normally associated with liquid, you know that, right? That means you sometimes on some certain surfaces, if you drop water, water will not move away, right? Which I showed you on the lotus leaf. I showed you, right? It won't move away because of surface tension, right? So surface tension is basically a property of a liquid to retain that shape that has the minimum energy, right? The spherical shape. The general tendency will be a spherical shape, right? So that is the tendency that happens at the surface. Okay, it's a surface. That's why we call it a surface tension. Okay, it's a activity happening at the surface. Similarly, surface energy. All right. So surface energy basically talks about that energy needed to keep it or retain it at that particular low energy condition. Okay, that means the say a water droplet. All right. So the water droplet is staying as a droplet because of the surface tension. But the amount of energy that has been consumed to retain that water droplet shape, that is the surface energy. All right. Okay, so looks dangerous, right? But nothing to be really dangerous about. We studied these in physics. We talked about entropy and enthalpy, right? So entropy, of a system we say is always constant, right? So the extra energy possessed by the surface atoms is described as surface energy that I already talked about, the energy that is involved, or in other words, this is what is referred to as the surface tension. So the surface energy is the energy required to create a unit area of a new surface, right? I told to create that surface, the amount of energy involved is surface energy, right? So if we express surface energy with this symbol called gamma, then gamma is the rate of change of the Gibbs free energy with the area. All right. So what is Gibbs free energy is defined as the energy portion of a thermodynamic system available to do work. Right. So a typical thermodynamic means the variation in temperature. Okay. There's a variation in the heat content. So if you have to use that for doing some valuable work, then this is the formula for calculating the Gibbs energy or free energy is given by Z equal to H minus Ts, where H is the enthalpy, S is the entropy, and T is the temperature in Kelvin. Okay, going back to physics books, but don't worry much about this one, just a concept now. As far as this course is concerned, we are not going to all these intricacies. All right, you don't have to worry about that for your exam also. This is something just to explain the concept. I hope you understand our these terms, entropy and enthalpy. Let me see if I can explain it in a different way. Say, all right, let's look at it like this. Say, now suppose you people and me, all right, say we are talking, you people are in your maybe early 20s, right? 20, 21 maybe, or even less. And I'm 50, okay? Now we fall in two different category of people as far as energy is concerned. Naturally, it is expected that you guys should have much more energy as compared to me. That means if you're playing football, you should be running around more in the field as compared to me because I will start having fatigue. I'll get tired, right? So if I say that, suppose now a group of friends, you are, in your peak, very energetic, you are playing football, okay? So a big playground is not a problem for you, no? You can run around and you need a full football field. For old people like us, we might say no, make the football field half for us, right? So when these people, like you people becoming my age, you are going to go old, then you become less energetic, okay? And then what you might need is a small corner table for you to sit and have coffee and remember your youth, right? So the memories of those days when they were more energetic and you always wanted to wander here and there. So those are memories now. Now to think about it, when we're doing all this energetic work, right? there was some amount of restrictions. I mean, there was some amount of, say, suppose you want to go somewhere to play a match, a cricket match maybe. You have your own team, right? You naturally have to ask permission. At this age, you are going to talk to your parents, say, I have to go to Delhi for a, national level cricket tournament. So you need permission to go there. You just can't walk out, right? At this your age, even though you have the energy to do that, right? So why do you need permission from your parents? Because obviously who will sponsor you? If something happens to you, who will make all the arrangements for you? You're in Delhi, who will constantly be in touch with you? If some problems arise, you have some money issues, who will transfer the money to you? All those things comes there, and that's why you are not at your free will to do everything. All right, there is certain control on you. All right. Uh, so this example actually is from a social life I'm trying to pull in. It may not show resemblance to the physics on the whatever is on the screen, okay, enthalpy, entropy, but it does have that, you can say, analogy. You can say the analogy is there. We can imagine energy of young or old people as their enthalpy. All right, the energy that you possess, the energy that I possess, we can consider that to be the enthalpy. Okay, which is in a sense also indicative of the desire of liberty or freedom, while limiting or reducing someone's liberty. If I have to reduce, like, your parents saying, no, 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 you cannot go now. Okay, you cannot go and play the match now. I cannot send you now, or some issues there. Corona is there. I don't think you should go. And you cannot go unless they give you permission, right? So reducing liberty or putting a ban on someone's freedom. So this ban can produce an anger, right? You might be very angry. You will slam the door, walk out. So you can say, how do I? So that one, like, you slam the door and walk out, you are transferring your energy, all right? Uh, so you'll say the anger, okay? That slamming of the door, maybe a few, screamings from you. No, you always do that to me, all those things happening. It's a release of the energy, all right? And this can be a direct result of the enthalpy, right? So you can say that increasing someone's liberty or allowance or freedom is equal to increasing the entropy, all right? Which consequently results in the reduction of someone's anger. If your parents had said, okay, okay, you go, you won't have slammed the door, or you won't have shouted out, or you won't have reacted, right? So, that will cool down the system, okay? If you, that means your restrictions have been wider, you will be a cooler person, all right? So that is sort of what we are talking about, enthalpy and entropy, right? You have a wider domain, entropy is bigger, all right? So if the entropy is bigger, your enthalpy is less, right? That means you are a cooler, you are not very excited, you are not very angry, okay? So that sort of is how you can understand the relation between entropy and enthalpy, okay? Anyway, I don't know if I could get it delivered to you, but don't worry much about this slide for the moment, okay? So cohesion, adhesion, and surface tension, okay? These are important terms to study the behavior of nanoparticles, okay? Or any material as such. So the cohesive forces are those that hold the bulk of the material together, okay? The bulk. So they're together as long as the cohesive forces are in play. So they are forces between like atoms or like molecules, okay? The same type of atoms, the interatomic, attractions, repulsions, all those coming in. So surface tension is the result of enhanced cohesive forces, all right? So the cohesive forces, take it to nano size, there will be even more enhancement in the forces. So all these happening, they directly relate to the surface tension. adhesive forces are attractive forces between unlike atoms. Now, when we're talking about cohesive forces, we're talking about like atoms, the same type of atoms. But if it is between atoms of two different materials, those we call as adhesive forces. Okay, so this always happens at the interfaces. All right, you understand about adhesion, right? Something you put on a surface and it gets stuck there is because of the adhesive forces happening there, right? Sometimes if there's water on a surface, say your kitchen table, put some water and put a small piece of glass, maybe even your refrigerator glass. If you're washing or cleaning your refrigerator and you put a wet glass on your kitchen table, you might find that it's very difficult to pull it out. You may have to slide it to one side and then pick it up, right? That is happening because of the adhesive forces coming into play. Contact angle behavior is an indication of the strength of these forces, all right? The cohesive and adhesive forces. So contact angle basically talks about uh, the hydrophobicity of a material. Okay, so like the water droplet forming. So what part of the water droplet is actually in touch, and this shape, I'll show you the figure somewhere. I should have it. What is called as contact angle. So if the angle I'll show you is more than 90 degrees, then it's a non-wetting case. That means a super hydrophobic surface. But if it's less than 90 degrees, then we say it is a hydrophilic surface. That means it loves water. The water will spread out and water will remain stuck to it. But if it is above 90 degree, actually, above 90 degree, we call it hydrophobic. And if it goes above 130, 140 degrees Celsius, we call it a super hydrophobic. Okay. So all these come to play in the surface. Right, so you remember all this when you say that this is the angle we are talking about. Okay, at the surface, the how the surface remains. Okay, so this is because of surface tension. If you remember mercury, we had put in this in your physics practicals in school. Water will make a different angle, mercury will make a different angle depending upon the density of the liquid. You will have different contact angles. Okay, anyway, this is just to make you understand. Talking about the surface of water. Water is a very, very interesting material. So, just a minute. Let's do one thing, guys. I have 10:30. I have to move to the meeting now. So we'll continue in the next class. Let's see if I can pull in one more class this week. But of course, with your consent, I'll ask you guys if we can have another class in the evening. Okay, and because there's a lot, because we started a bit late now. So I'll let you know. Maybe this week we'll have one more class. Okay, and we'll continue and finish this lecture in the next class. Okay, so thank you everyone. Yeah, and you submit your attendance, please. Okay. Thank you, guys.
Thank you, sir.